So we're going to talk a little bit about hybridization, which is kind of important to understand why molecules have the shapes they do, and how things bond a little bit more clearly than looking at just atomic orbitals. Okay, so that's our focus here. Take methane, for example. So if you keep the orbitals around the carbon and the hydrogen separate, you're going to have some variation, right? Because from hydrogen's 1s to carbon's 2s, you get one kind of bond. And then for hydrogen's 1s orbital to carbon's 2p orbitals, you're going to get a different kind of bond, right? So that should give you different kinds of bonds. But we know that all four bonds in methane are exactly identical. So the question is, how do we know that? Well, there's this thing called bond energies. You can measure how much energy is required to break the bonds, and it's the same for all four bonds in methane. It shouldn't be, because there's different kinds of orbitals in carbon. And so some of the orbitals are s orbitals and some are p orbitals, and they're bonding with the hydrogen in a different way if we go with the strict atomic orbital model, okay? So the other problem is the geometry of methane. We know that methane is tetrahedral with 109.5 degree angles, but the p orbitals in carbon are all perpendicular. They're 90 degrees from one another. So that doesn't jive either. So there needs to be some other way of doing this, okay? This is a picture over here on the left of the different orbitals that are available to us, the s orbitals and the 3p orbitals, and you can see that they're in very 90 degree orientation, or the s orbital is 360 degrees symmetrical. But the methane molecule here on the right, you can see, has a tetrahedral shape. Okay, so there's a problem here. We've got to figure this out. The way this works is that carbon basically has to create a new set of orbitals. It can't just use its 2s and 2p separately. It has to create four identical orbitals that have to form that tetrahedral shape. And the way it does this is by something called hybridization. So hybridization literally means to mix. Okay, we're mixing normal atomic orbitals to form what are called special molecular orbitals, or bonding orbitals. Okay, so here's how this works. In methane, CH4, we need to create something called sp3 hybridization. Okay, the sp3 designation tells you what has been mixed together: an s orbital and 3p orbitals. If you take one s orbital and 3p orbitals, you get a total of 4 new hybrid orbitals. Okay, they're identical in shape. They have one large lobe, one small lobe, and they set themselves up as a tetrahedral arrangement, 109.5 degrees. Okay, so they look kind of like this. It's a weird sort of looking shape. It doesn't look like a p orbital anymore. Okay, and that's because we've mixed in some s orbital character to that. So if you need 4 tetrahedrally arranged orbitals, you have to hybridize as sp3 hybridization, 1s and 3p. Okay, so here's what it looks like. We hybridize the s and the 3p orbitals from carbon on the left. We hybridize them, we get 4 identical orbitals, which all have a large lobe and a small lobe, and they're pointed to the points of a tetrahedral, 109.5 degrees. If you look at the bottom half of this diagram, we can see sort of the atomic orbital filling diagram notation, where on the left here we have the carbon's atom by itself. We have the 2s and then the 3,2p orbital slightly higher in energy. When we hybridize them, those 4 orbitals are redistributed, and they become 4 equal energy, degenerate sp3 orbitals. The energy of the sp3 orbitals is in between where the 2s and the 2p were, although it's a little closer to 2p because there are 3 of those in there and only 1 2s in there. We had 4 new orbitals. The original 4 electrons that were in the 2s and the 2p orbitals of carbon, 2s2, 2p2, are now 1 electron in each of the sp3 orbitals, as according to Hund's rule. Okay, so now a methane bonding picture looks a little like this. The blue sp3 orbitals are the carbon hybrid orbitals that it just made. The hydrogens don't have p orbitals. They only have s orbitals, so they don't hybridize. And so you've got a little overlap between the 1s orbital of a hydrogen atom and the sp3 orbitals of of the carbon, and that creates something called a sigma bond. This overlap allows you to share the one electron that was in each sp3 with the one electron that hydrogen has to make a pair of electrons shared in this new orbital. And that's how sp3 hybridization works. Now in C2H4, okay, C2H4 is ethane or ethylene. There's a Lewis structure for it. You'll notice that each carbon only has 3 domains, 3 bonds that it needs to form. One of those is a double bond. We'll get to that in a second, okay? So I need 3 orbitals. Well, if I need 3 orbitals, I'm not going to mix an s and 3 p's. That gives me 4 orbitals. I'm going to mix an s and 2 p orbitals. And that gives me 3 new hybrid orbitals. Again, they're all 3 identical in shape. They've got one large lobe, one small lobe. But because there's only 3 of them, they adopt a trigonal planar arrangement, 120 degrees. Okay, so if you need 3 identical orbitals in a trigonal planar formation, you're going to sp2 hybridize them. Okay, the orbital looks the same. It's still made of s and p orbitals, so it still has the large lobe and the small lobe. Okay, so we mix the s and 2 of the p's together, we get 3 identical orbitals. They happen to be 120 degrees apart from one another. And in the bottom picture, you see the same sort of hybridization. But notice over here on the right, now we have this 2p orbital that we didn't use in our hybridization. It's right there. We've got a 2p orbital that wasn't used. Well, what's gonna happen with that? Okay, here's the sp2 orbitals overlapping with the hydrogen 1s's to create what we call, again, sigma bonds. This sp2 orbital can overlap with this carbon's sp2 orbital, and they can share a pair of electrons. There's another sigma bond. But what about this unhybridized 2p orbital that we didn't use? Well, that orbital is also on the other carbon, and it's perpendicular to this trigonal planar business. It side overlaps, forming something called a pi bond. Okay, so it looks kind of like this. There's the unhybridized p orbital in this carbon. There's the one in this carbon. They are going to side overlap, side to side, and share a pair of electrons to make what's called a pi bond. It's not 2 bonds. It's only 1 because it's created from 2 orbitals. 2 orbitals are needed to make 1 bond. Okay? So the sp2 orbitals can share electrons in between 2 atoms. They can share electrons with the 1s orbitals from the hydrogen. Okay? And that's the sigma bonding. So we get sigma bonding when we get head-to-head overlap, and we get pi bonding when we have side-to-side overlap. Okay, so this is a complete bonding picture of C2H4. You'll see the sigma bonds between the sp2 and the sp2 of carbon, or the sp2 and the 1s orbitals of hydrogen. And then you've got this side-to-side bonding between the unhybridized p orbital, and that's our pi bond. Okay, now, the pi bond, because it's above and below the plane, creates sort of this generalized area where you're going to find electrons above and below the plane of the molecule. Okay, so that pi bonding is really, it's not just like 2 orbitals anymore. They sort of merge together to form these 2 little balloons of electron density. So each double bond, every time you have a double bond, you're always going to have 1 pi bond and 1 sigma bond. Single bonds are just sigma bonds. Everything, if you have 2 atoms connected, they have to be connected by at least 1 sigma bond, and then the rest are pi bonds. Okay, so there's how we write that, the notation for that. CO2, there's a picture of CO2. Now CO2, carbon has 2 bonds coming out of it. So we only need to make 2 bonds, and they're in a linear arrangement. So I'm only going to miss 1 of the s orbitals and 1 p orbital to make 2 identical orbitals. Okay, they'll have a linear arrangement, 180. So if I need to make 2 bonds, 2 linearly arranged orbitals, I use sp hybridization. Same shape, because it's still mixing an s with a p. So this is what that looks like. Okay, get a linear arrangement. And here you can see the hybridization. We only mixed 1 of the s, or the s and 1 of the p orbitals to get our 2 sp orbitals. The other 2 p orbitals haven't been touched. So what do you think they're doing? Okay, here's the sp2s, okay, for oxygen. Notice oxygen's hybridized too. Here's the sp orbitals for carbon. You've got an overlap there and an overlap there, head-to-head overlap. Those are sigma bonds. What do you think's going on over here in these sp2 orbitals? We'll have to think about that for a second. Okay, the unhybridized orbitals are going to be perpendicular to each other and also perpendicular to these sp, and so they can have side-to-side overlap twice. So it looks like this. This is a complete bonding picture for CO2, where we have the sigma bond in between the carbon and oxygen head-to-head along that internuclear distance. And then these p orbitals that haven't hybridized, they side-to-side overlap. There's a double bond on this side. And then these two are sort of twisted 90 degrees from these two, but they also have a side-to-side overlap, which is another pi bond. Okay? So what's going on in these seemingly unused sp2 orbitals? What does oxygen have on it? It has lone pairs. The lone pairs are there. Okay, so some important points to think about. Head-to-head overlap is a sigma bond. Side-to-side overlap is a pi bond. If you have a multiple bond between any two atoms, you've got one sigma bond in there, and then the rest are pi bonds. So a triple bond, one sigma bond, and two pi bonds. You can figure out an atom's hybridization just by looking at how many sigma and pi bonds there are. 4 sigma bonds, no pi bonds, that's sp3. 3 sigma bonds and a pi bond, that's sp2. 2 sigma bonds and 2 pi bonds, or 1 sigma bond and 2 pi bonds, sp. Okay? Other things. All atoms in a molecule have to hybridize. And you saw that with the oxygens. Even though the oxygens weren't in the middle, they still hybridized to create the right orbitals. Okay? Hydrogen doesn't do this because it only has an s orbital. It doesn't have any orbitals to mix with it. A lot of times you're going to have to draw a Lewis structure to figure out the hybridization. So you got to be good at that. Lone pairs can be in hybrid orbitals. So if you have an atom that has lone pairs on it, those lone pairs are in hybrid orbitals. Okay? Most cases. And then the geometry of the molecule is determined by its hybridization. sp3 is always tetrahedral, sp2 is trigonal planar, sp is linear. Okay? So that's basically the whole thing. What about extended octets? What about something like SF6? 6 sigma bonds? As it happens, they used to think that d electrons were involved, d orbitals. Recently, within the last few years, so research has shown that that's not actually the case, and it's fairly complex. So we don't consider those anymore. We don't care so much about what's the hybridization in trigonal bipyramidal, for example, or octahedral. We don't care. It's not important. The only ones you have to know are sp3, sp2, and sp. Okay, so you got those, you're good to go.